Hey there, welcome back. I'm going to teach you about electron configuration now and how that goes hand in hand with what we learned in our last video. Anyways, electron configuration has to do with valence electrons. So we need to talk about what a valence electron is. So, valence electrons, new color, are the electrons that are able to be used in reactions between elements. I'm not going to say that they are the electrons in the outermost shell because that is only applicable to certain elements. There are exceptions, and that's the transition metals actually. The transition metals are the ones that demonstrate the difference, and that's why your teacher says that it's hard to know how many valence electrons or the ionic charge of anything that has a transition metal in it. Anyways, valence electrons, if you want the basic understanding, the electrons in the outermost shell, but if you want to go deeper, it's the electrons that can participate in reactions and bonding, which is essentially the ones in the outermost shell, but it sometimes applies to the ones that are just underneath, that are in the shell below. So anyways, let's draw it. Let's have a nucleus. And let's say it's like hydrogen, and it has one valence electron because it only has one proton, so it has one electron. How many valence electrons does it have? One. It's just the total amount of electrons in the outermost shell. The amount of valence electrons something has is not influenced by how stable it is. So hydrogen, which is this, can bond with like everything. Meanwhile, you have helium, which has two electrons, which means it has a full shell and subshell, because remember the first shell only has one subshell, and that subshell can hold two electrons, which means the subshell itself can only hold two electrons. It means it's full, so it's a noble gas and is very, very stable. But that does not change the fact that it has two valence electrons. Those are the ones that can participate in activities, special activities. Anyways, that's what a valence electron is. When you want to get more complex, let's say I have something bigger. Boom, 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 boom. Whoop, whoop. Let's the third one. I think we would actually need a fourth one. But let's say my valence electrons are in this shell. Remember that to fill up, generally the shells below have to fill up first with electrons. So you start filling from the bottom, like electrons, and then have some electrons in this one. They're just kind of floating around. Some of these that are close, depending on if this shell, the D subshell, is full or not, they can jump out if needed to be valence electrons as well. The reason why there's different ionic charges on transition metals is because these are like reserve valence electrons. They don't have to be used. They're just kind of hanging out. So, how does this look, or how do we describe this? So, remember how, well, actually we need to talk about some terminology. Ground state. A ground state atom is an atom that is in its non-ionized form, which means it's not excited. There's the ground state and the excited state. I'm going to write this. Ground state and excited state. So, ground state is just a basic atom, like here is a hydrogen atom, do what you will. So, remember back to how atoms were put together and how every atom has a certain amount of protons, and that's what determines its what atom it is, like what element. Well, every single ground state atom is going to have the same number of electrons as well. So, if I have, I don't know, let's pull out a periodic table. Boom, 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 boom. Periodic table. Let's say I have sodium, which has 11 protons. That means it's going to have 11 electrons. Easy. So, That means we know exactly how much to fill our orbitals with. You know, we're gonna have to fill our s orbitals on the first subshell, and then the s and p orbitals on the second subshell or on the second shell, and so forth until we reach the point in which we have no more electrons. It's kind of like this. You fill up the containers. So I'm gonna draw the graph from the last one. So remember, this is n equals 1, and it's p, and then this is n equals 2, and it's going to have s and p, and then n equals 3, and that's going to be SPD. Now we're going to see how much it's going to fill up. So we have one open orbital here, one open orbital here, two open orbitals here, three. Yeah, we have three open orbitals. One, one, two, three, 1, 2, 3, 4, 5, 6, 7. Pretend that didn't happen. Anyways, we have 11 valence electrons at our disposal. So what we're going to do is we're going to just fill it up. So we have 1, 2, 3, 4, 5, 6. Nope, I made a mistake. You have to fill up the orbitals in order. So this one gets 1, 2, and then 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. So we filled it up. Now, what does that tell us? It tells us one thing: the electron configuration and how we're going to notate it. So how do I write this in like a sentence or an equation? What do I put down? It's going to be this. You're going to write every subshell, or every shell, every subshell, and how many electrons are in that subshell at once, using this notation. You're going to have a coefficient, the letter of the subshell, I'm just going to put S for an example, and then you're going to have X being the amount of electrons that are in that subshell. Yeah, so let's go along filling it up. So we're going to start with 1, so shell 1, subshell S. How many electrons? 2, so 1s squared. And then we're going to have a space, just a space, doesn't really matter. It's not plus or anything, it's just space. And then we're going to get to shell 2, 2s. How many shells does 2s have? Or electrons shell subshell 2s have? 1, 2. Remember, an S subshell can only have a max of 2, so it's never going to go above that. Next is SP, which has 1, 2, 3, 4, 5, 6. So 2p exponent 6. Then we're going to go up to 3, so 3s. And S always has 2, and we know that one's full. Wait, no, 3s isn't full. I misread. So look, 3s only has 1, so we're just going to say 3s1. And that's the electron configuration. Easy as pie. So it does get a bit more complex than that, but this is how you basically write the electron configuration for an element. So, the next level of this is the noble gas configuration. So that sounds scary, but what it is it's a shorthand. So imagine you have a really long element like, I don't know, look at the periodic table, indium, which has 49 valence electrons. Are you really going to write all of the 1s, 2s, 2p, 3s, 3p, 3d, everything? I don't think so. There's a faster way to do it, which is to use the noble gases as placeholders for configuration up to that point. So imagine you have a periodic table. And you have your periods. Boom, boom. It's not really perfect, just pretend it is. 1, 2, 3, 4, 5, 6. Hey, I did it right. Anyways, in each period, you're going to have a noble gas on this end. Helium, and then I think there's neon. Yeah, I was right. Neon, argon, krypton, xenon, and then radon, and then oganesson. Og. That's a fun one. Anyways, so if we see how many valence electrons they have, which is going to be full, all we have to do is say, oh, I could have written the configuration for this, but I'm just going to say that's what means configuration. So how do you use this? Well, say I have, we used sodium, which sodium is right here. Yes. So instead of writing everything like from here to here and then like 1 valence electron, 2 valence electron, 3, 4, or just electrons in total, 3, 4, 5, 6, 7, 8, I think, we can write up to neon by simply saying inside brackets neon and then just whatever is on the row. And so sodium is right there, so it's just going to be 3s S1. If you see, I just cut it off right here because this is where shell 2 filled up. Remember how I said that each period is a shell? Like this is shell 1, 2, 3, and so on. That's where it comes from. So I can essentially do a shortcut. Now let's say I wanted to do like cobalt, somewhere around here. All I have to do is go the period up, which is argon, and then all I have to do is write the configuration counting up here. So I just count from argon more and more electrons. Now, you would think that, actually no, I haven't made that connection yet for y'all. Anyways, remember how I said that shell 1, shell 2, shell 3, and shell 4? Well, they don't actually fill up in that order all the time. So you would think that it would go 1s, 2s, 2p, 3s, 3p, 3d, and then 4s, 4p, 4d, 4f, but it doesn't. It doesn't do that. Why? Because the energies are just whack. However, the periodic table is organized to help us combat this. So, I'm going to erase this, redraw the periodic table. So, what you know now is how to write electron configuration and this noble gas configuration. And now we're going to learn, I already forgot, what is it? Oh yeah, the blockings. Where they go. Yeah, blockings. So, I have my periodic table. Three. Easy. 1, 2, 3, 4, 5, 6, 7. Easy as that. Anyways, we have periods 1, 2, 3, 4, 5, 6, 7. Now, we have to talk about what the main group elements are. The main group elements are the chill elements, the ones that like don't cause problems for us. The easy ones, which are going to be, actually I forgot the lanthanides and actinides. I'm just going to pretend those guys don't exist. Okay. The main group elements are within these blocks. Purple, just so you can kind of tell where it is. So this and this are our main group elements. And that's easy enough to remember. Like it's just chunk, transition metals suck. And yeah. However, they're not just saying, oh yeah, it's because the transition metals are weird. We can actually use these to show which subshell is which. These are called blocks, by the way. So this right here is the S block. This is because the S subshell fills up first. Hydrogen, remember, the subshell that's first. This is the P block, right? P. So this chunk of the periodic table is called the P block. This, the transition metals, are the D block, and this one down here is the F block. No one cares about the F block. So why is it like this? Well, remember that the periodic on the thing, electrons fill up from the bottom up, and each shell only has a certain amount of subshells, depending on which one it is. Like n equals 1 has one subshell in a second. So the first period, is the first shell, which only has one subshell. So it's not going to fill up any more than 2 electrons. Helium is kind of weird, like we just kind of pretend it's over there in that block. Helium belongs in the S block, but it's an exception. Beyond that, 2, we know that the 2 block doesn't fill up, the D block isn't going to fill up on our second shell. It's going to go S, and then it's go P. So you're just kind of reading left to right, left to right. And you get to 3, and then this is where it gets whack, and you get confused. And I'm going to demonstrate why it's actually not as whack as you think it is. First, it's because 3 is going to fill up 3S and then 3P. Where did 3D go? 3D, would it be over here? Because the P block is already full, but we don't have any more to fill up. Well, once we get to 4, or period 4, then we start filling up our 3D. So we're going to go 4S, then 3D, as we write our electron configuration. And it's going to continue on. So 4S, 3D, 4P, 5S, 4D, 5P, and then F block slides in right here, second to bottom period, 6S, then the F block is going to be 4F, 4F, and then 5D, and then 6P, and it's already just devolved into what it is. But I hope you can see, you can follow the periodic table to know the order in which your subshells are going to fill up. That's all it is, just what order are they filling up in. Now, what's cool is that every group of the elements has the amount of electrons that subshell can hold. Remember how S can only hold 2 electrons? Well, lucky for us, the S block can only has 2 columns, 2 groups. The P block can hold 6, and it has 1, 2, 3, 4, 5, 6. It's perfect. So you can count up to the thing and say, and then once you get to it, count within the block to find how many electrons it's going to have. Then it's the same. Wait, where was I going? Yeah, same with this one. If you count, there's only 10 elements in our transition metals, or 10 groups in our transition metals. And in the F, there's 14, which is kind of weird because it's technically 15, because lanthanum and actinium are actually fit in over here, but property-wise, they do better in the F block. It just fits better. Like lanthanum, actinium, and helium are the special cases, the special children. So I hope that makes sense. Let's do an example. So I'm going to choose vanadium. Yeah, vanadium works. So vanadium is right here, and it is, it's the third one. V, yeah, just V. So we're just going to go along, and we're going to write our configuration. I'm going to do it in purple. So I know we have the first row, so it's going to be 1s, and it's just all the way full, so it's a 2. we have 2s, which is going to be these two, and it's full. 2p, because it's in the p block, so I've gone from 2s to 2p. 2p, and it's going to be full, so it's 6, and you can see how we fill it up 1, 2, and then 1, 2, 3, 4, 5, 6. So this would be the configuration neon, but it's not. So 2p6, 3s, 2 because it's full, and then 3p over here, 3p6 because we got 1, 2, 3, 4, 5, 6, and then we get down to 4s, and then we know the s block is full because we still haven't filled up our electrons to get to vanadium. 4s, 2, and remember, this is going to be 3d. That's when 3d starts filling up. So 1, 2, 3. Vanadium has 3 electrons in its 3d shell. 3d3. Now I'm going to teach you how to know how many valence electrons are in the element. So remember when it was, oh, how many are on the outside? Well, this is the outer shell, 4s. However, 4s is not full. 4s is full, but the fourth shell is not. So the 3d is almost on the outside. It's very close to the 4s. So vanadium has 2 official valence electrons, and then 3 other electrons that are like extra electrons. These are going to be like your reserve valence electrons. So RVAs or VEs and RVEs, reserve valence electrons. I hope that makes sense. So what this actually does is you can now count the groups to know how many valence electrons or maximum valence electrons a thing will have. So I'm looking at the periodic table here. We have our group numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, yeah. Yeah, wait, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so it's going to be 12. And that tells you how many valence electrons a thing has. So if we're in the first column, or the first group, group 1, so it's 1 valence electron. Group 2, 2 valence electrons. Group 3, technically 3 valence electrons, because it's going to have 3d1 plus the 4s2. And the 4s is what's in the outermost shell. Like 4s, n equals 4. It's going to have the 2 valence electrons in here, and then d is going to have 1. So it's going to have 3, you know? And then it just keeps counting. Group 3, 3 valence electrons. Group 4, 4 valence electrons. Group 5, remember vanadium, 2 plus 3 is 5. Group 5 is 5 valence electrons. But remember, these are reserve valence electrons. And that's where you get the charges on your ions from, because your ions don't have to use these valence electrons. It's like having 2 forms that your element can evolve into. It can use 2 of its electrons and have a third one just kind of hidden away, and then bond as a 2 plus ion, or 2 plus ion. Or it can use the third valence electron and be like, hey guys, I have 3 valence electrons now. And that's how it works. You know for sure that these are going to be valence electrons, and this one maybe not. So I hope that makes sense. That's more or less as complex as it gets. There's one other exception that we're going to talk about, which actually isn't super bad, and it will actually make sense considering this. Just a new concept of how atoms want to be stable. So remember that atoms and molecules want to be stable. They don't want to be jittery. They want to do what takes the least amount of energy for them to not be moving. They just want to be at rest. So let's look back at the orbitals. There are 2 stable orbitals, a half full orbital and a completely full orbital. So let's say subshell, not those are the stable things. A completely full subshell or a half full subshell. Let's choose D. D has 1, 2, 3, 4, 5 orbitals. This is the D subshell. On any of them. Like, it doesn't matter which thing you're in. So, if I fill up my D subshell with valence electrons, it's going to go 1, 2, 3, 4, 5. Boom, it's half full. And the atom likes that, which means that this is going to be a particularly stable element, at least chemically. This applies to manganese and technetium. If you look at the periodic table, you're going to see that they have 5 valence electrons, or configuration rather. It's going to have 5 valence electrons in its 3d orbital. Or not 3, but just its d orbital. Which means that it's going to be just, I don't know, more chill than the elements that are around it. And if you fill it up even more, we're going to get to group 12, which are zinc and cadmium and mercury. Since they're completely full, they're also going to be like, I'm chill, man. I don't have any problems. And it's going to be very hard to actually pull an electron away from them or give one to them because they're like, nah, I don't want any more. To make them stick or to pull them out is going to take a lot more energy than anything else. Now, what about elements that are barely full or just 1 over? So let's say I have my d orbital and it's 2, 3, 4, 5. And 1, 2, 3, 4. And I'm missing 1. I'm almost full, but not quite. This would be chromium and molybdenum, actually. So in our d orbital, we have chromium and molybdenum. Chromium only has 4 valence electrons in its d orbital, or its 3d orbital, and molybdenum has 4 valence electrons in its 4d orbital, subshell. And they would rather be full. So, remember this. Our d orbital is right here. The d orbital is right here. Right above it is a handy-dandy 4s orbital. So, what it's going to do, and this one's going to have 1 or 2 electrons in it, because that's how many it can hold. What the element is going to do is it's going to take an electron from the row above it to fill itself up. And, of course, for the complete one as well. This is the half-full one, which would be chromium and molybdenum. It's going to steal the element, or the electron, and make itself complete. What this looks like is the ideal configuration for these elements would be chromium is argon. I'm just going to use a noble gas notation. Argon, 4s2, and then 3d4. 3d4. Now it wants to have 5. It wants to be half full. So what it's going to do is going to be like, hey man, I'm going to take an electron. So all of a sudden it becomes 4s1, 3d5, because 5 is a happier number because it's half of that complete number. It's half full. So that's where we get our exceptions from. So this is chromium. You can do the same thing for molybdenum, which is what's below argon, krypton, where it's going to be 5s1, 3d5, and it's going to be happy because it stole an electron from there. And the other ones, which are the full ones, or the almost full ones, are going to be copper and silver. So look, we only need 1 more to complete it. Copper is going to look like, copper is also argon. It's going to be 4s2, 3d9. Ideally, that's what it would be, but because it wants to be complete, it's going to steal the electron from the shell above, and it's going to become 3d10 and 4s1. Important to note is that the elements that do this have only one ionic thing normally. Like, of course, there's going to be weird exceptions and weird conditions, but in a general chemistry, introductory chemistry course, it's going to be that, which means that manganese is going to have how many valence electrons? 2 valence electrons. It's not going to have 7 or anything. Wait, no. 1? Yeah. Because they have full, so those 5, because they're stable, these 5 or 10 don't want to go anywhere, so they're not going to be used in bonding. So 1 valence electron. Easy. Because that's the one that's in the 4s orbital still. There's one other thing to cover with this, which is ions. How do you say, write the electron configuration of ions? It's this. So we know that oxygen can have ionic charges. So the regular valence configuration of oxygen is helium, because it's that, and then it's in the second row, so it's 2s2, 2p4, if I'm not wrong. Yep, 1, 2, 3, 4. That's in the fourth column, so 2p4. Easy. So, wait, no. Oh, that's carbon. It's going to be, yeah. Yeah, it's going to have 4. And it'll have 6 valence electrons. Yeah, because 4 plus 2 is 6. Yes. So, let's say it's an ion. What does it mean to be an ion? It means to not have an electron or to have extra electrons. Now, in reality, it's not that we've removed an electron and it's floating off somewhere else. It's that it's bonded, or it's aqueous. It could be aqueous or it could be bonded with something else. It's like this is the tendency it will exhibit. But I'm going to speak in terms of we just kicked an electron out or we just brought another one in. So let's say O2 minus, which means it has a charge of -2. Every charge is going to be an electron, which means that our oxygen, which is this, O, is going to have +2 electrons. So what does that do to our configuration? Well, since the configuration is just the count of how many electrons we have, we need to add 2 to it. So, what shell can we fill up? 2p6. We have more electrons. And that's it. When you have ions, you just move it around. When you take electrons away, like oxygen wouldn't do this, but let's say it was 2 plus, and it was originally 4, we're going to go down to 2. This means that electrons can have the same configuration, or elements can have the same electron configuration as other elements when they are ionically charged. And that's it for this video. That is all about electron configuration. There's a bit more that I can't quite remember that I'm going to review right now, but this is more or less what you need. Easy. Anyways, I hope that was helpful.